Good morning, I'm Abhishek and this is Rahul. We're going to be presenting the second paper today. So let's just start off with a few clips that I have for you. The previous one. This one.
Is that playing?
Oops.
Oh, look, I'm singing something. I'm singing a dress. Well, it doesn't matter, you're honest. Is there a bonnet? Aha! Nose down, Harry. June, these are speak for you.
Not only that, it's ghastly.
What are you on about?
They're not for Ginny. They're for you. Dress robes.
Dress robes? For what?
Right. So what kind of behavior do you feel was there in that video? What did you see? And what kind of behavior did you see?
On the range of typicality to atypical.
What were the people doing there?
Walking around.
Walking around? What was wrong about that?
Yeah.
Right. What was
Surprised, annoying.
Ginny doing?
She was kind of annoying.
Right. So, would you say there was something weird going on here? There was something, or was this normal? Would you say this is, people were normal, people behaving normally? Or would you say there's something weird, there's something off about how they're behaving in that video? Normal. Right, great. Let's go to the second clip.
To stare through the peephole for 3 hours. You're gonna get peep eye.
I knew it. I always knew she liked him. She'd say no, but here we are, right? We just broke up. First thing she does.
You didn't just break up.
Hey, it's been like 3 weeks.
You slept with somebody 3 hours after you thought you broke up. I mean, bullets have left guns slower.
Yes, well, if she kisses him goodnight, I'm going to kill myself. I swear. I can't watch this. Date over. Oh, here we go. She's going in. She's going in. He's going in. He's going in. The door's closed. I can't see anything with the door closed.
Right.
Okay.
So what kind of behavior did you see here?
Louder?
Louder. So
No. Can you say it a little louder?
It was louder.
Oh, you can hear it now.
He was frustrated, but then he was over-exaggerating the...
Subpar acting.
Right. So
Their mouths move.
So there's a guy he's really exaggerating stuff. He's peeping through the peephole and he's talking, right? Would you say that's normal? Generally, forget the context. Is that normal?
Probably for stalkers.
Probably for stalkers, but not for. Is that normal behavior? No. But this guy's just been through a really bad breakup. He's clearly not over it. So wouldn't we cut him some slack? Would you still say it's weird? Or is it normal? Kind of normal. Kind of normal.
Is it normal?
So so if taken out of context, that's really weird. That's not normal. That's not normal behavior. But in this context, maybe normal. Next week, please.
Drop the gun.
Oh. Sure, you just take off your little mask and show us all who you really are. Hmm?
Let her go.
Very poor choice of words.
Right. So we all remember this scene. So what kind of behavior is here?
For Batman or for Joker?
Whoever. Let's look at the Joker.
Okay.
What sort of behavior is that?
Morbid sarcasm.
Sarcasm.
Yeah.
Not things you associate with normal human behavior, right? So we saw the first clip, which most of you agreed was normal, typical behavior, no doubts. Second one, maybe we put in context, again, normal. Third one, everyone agrees, not normal, atypical. So how is it that you guys were able to decipher this? How is it that you knew that, you know what, this is normal, you know what, in this context, this is also normal, and this is normal? How is it that you guys came up with that?
I think based on the context we were able to judge the video.
Right, how do you get the context?
From societal conditioning that's been imposed on us from when we were born.
Right. So whenever we see people, we interact with people, when people behave, so there are these set of cues that they give out, right? They speak. You see set of visual features on them, you see some audio features. So those cues are somehow encoded, they reach us, and we have this mechanism by which we can decode those cues with context, and we can figure out what's happening. Now what do we do if we have to give machines the same capability? We want a machine to be able to tell what sort of behavior is happening. That is the entire focus of behavioral signal processing. So what BSP is trying to do is to give a window into the human mind, into our mental state, through whatever engineering advances we have. So we know to do certain things through whatever engineering advances we have. And now we've got to bring down this problem and solve it using what we know. So behavior, as I said again, behavioral cues can be vocal, they can be just the text, the content of what we're speaking, they can be visual. So behavioral signals can be overt, exactly what I just spoke about. My body posture, my gestures, my gaze, or they can be covert. You know, right now you don't know if my heart's pounding or how cold my hand is, so you don't know how nervous I am about this presentation, but those things would give you information about my behavior, about my current mental state, right? So how do we bring down this problem and make it into an engineering problem? So what do we know? We know how to solve signal processing problems, right? So we take these behavioral cues, convert it into a signal processing problem, and then, based on whatever domain-specific knowledge we do have, we apply it and we try to model these behaviors. So what that spits out is behavioral informatics. So what are we going to do with this behavioral informatics? Previous. Okay. Right. So these are the steps. The first thing is collecting data, right? So you have microphones, you have cameras, you have wires, you have sensors, you have virtual humans interacting, and there are multiple ways through which you can just collect behavioral data, right? Now this, you could do it in a natural environment like this, or you can do it in controlled environments like in a laboratory. The second step is to come up with low-level cues and signal descriptors based on whatever data we've collected. Those could be something like age, gender, the show features with which we're acquainted. These are the low-level descriptors. The final step of BSP is to model these, is to build a model for mapping these descriptors that we have to behavioral constructs. So how do we do that? We approach domain experts and we say, hey, tell me what sort of high-level descriptors constitute this kind of behavior. For example, I want to know what laughter means. How do I understand laughter? So I go to an expert and he says, laughter is so-and-so visual features combined with so-and-so frequency and this way of speaking and these gestures, right? So once I have this, I can map my descriptors to these behavioral constructs and build a model. And through that, I can not only describe what these behavioral constructs are, but in future, I can also do predictive analysis. I have an audio clip, is the person laughing at that? I have these capabilities. So where all do we apply BSP? Learning and training is one of them. So let's say I had something which is going to give me feedback. Right now, I'm talking to you, but I have pretty much no idea what each one of you is thinking, how you're feeling about what I'm saying to you. So if I had something to give me feedback about how I'm being perceived, how well I'm doing, where I need to go next, that would really help. That would make my talk more effective. Health and well-being. You're going for therapy. The therapist leans on his or her experience to speak to you, but let's say there was something which told the therapist that exactly how his or her patient is feeling, he would be at an advantage and he would be able to better help his patient. Same with customer care, automated customer care. If there is some way to know if the person who's calling in is really frustrated, if he's really patient, that would really help. You would know when to intervene. So what are the challenges of doing this? So this sounds great, right? I mean, it's got great applications, very interesting, but what's the problem in doing this? The biggest problem is the heterogeneity of data. No two people are alike, so no two people behave the same way. No two people respond the same way to the same stimulus. If I were to go up and punch each and every one of you, some of you would punch me back. Some of you would not do anything. Some of you would probably report me. Some of you would probably break down into tears. So how do we generalize and say, this behavior is in response to this? I could behave a certain way when I'm stressed. I could behave a certain way when I'm happy and relaxed. And this variability in data and behavior is one of the biggest issues.
So we should ask the group then, like how they would approach that.
Right? Yeah.
So
Yeah, the answer's on the next slide, so don't worry. Just in case.
we need an answer now.
Yeah.
How would you approach the heterogeneity in the data?
So what we're trying to do so far is just to feed it into some machine learning algorithms, come up with features, do signal processing, and ask this machine to tell me everything. What's the problem with that? No problem. We'll get it.
So
You can sample the data from different points.
from different people, like
Different
so
yeah.
more data is
More
one
data.
solution, right?
Yeah.
Like loads of data. Another solution would be the other thing, the opposite basically. So this is kind of bottom up, more data going up. The other thing would be
Try to limit down the class.
limited, or like go into literature, like identify what's really, like what people write about, like what do social scientists write about, like what is in the literature, go down, like find rules, what's important, to distill down like your problem into a smaller one. And so, yep.
Yeah. So that's a huge issue, right? Second one, especially when your observations are in laboratory conditions, or in laboratory, you get to control everything, right? So, there's no issue with the cleanness of your data. I mean, you don't get noise, it's completely observable environments in most cases, but in natural scenarios like this, you can get partially observable data, you can be noisy. That's another issue with your data. The third one, which is a little more subtle, is with subjectivity. So again, let's take up laughter. Laughter can be used to just show amusement, happiness, sarcasm, condescending. I can just be smirking. My laughter doesn't need to be vocal. There's so much variability in that, and its meaning is so different depending on the context that again is a huge issue. So the rest of the presentation is about how we deal with these challenges, and then we're going to have a look at one of the case studies that the paper talks about. That's going to be spoken about by Rahul. So,
Alright, so let me discuss how human judgments, first of all, can be improved by incorporating BSP into the human decision-making process. So, let's take an example of a child interacting with the teacher. The teacher, when she asks a question to a child, they observe them, they get to know their behavioral cues and verbal, non-verbal behavior. And based on that data, which they perceive somehow, they are able to make judgment about how to go about with the course plan, or how to better teach them so that they perform better. Now, let us try to incorporate the human decision-making process with the BSP somehow. so that the judgments received by the human evaluator or the teacher in this case, along with the available data, is converted to a model which gives feedback to the evaluator or the teacher here to better prepare the course plan or teach the child in such a way that they are able to perceive the information better. Or let's say in case of human well-being, a doctor may diagnose a particular disease better, like autism spectrum disorders, where pinpointing the exact location of the spectrum is really important for further diagnosis. So the authors of the paper, they summarize BSP in this very interesting way. They say that BSP is computing of human action and behavioral data for meaningful analysis by collaborative integration of human expertise with automated processing. And they stress on it to support the human decision-making process rather than supplant it. So my question to you is, should we restrict BSP to just supporting the judgments of human evaluators, or do you think that it can totally get rid of the human in the loop and work on its own?
Like we were discussing last time, if it's some critical action which needs to be taken, so in that case we need to be in the loop because that's a critical and it can decide a lot of matters. But if it is something like, okay, what can I have a meeting today with this person? The machine has the access to my calendar, so it can either say yes or no or something like that. So it totally depends on the type of application you're talking about and what's the context.
In some cases, right, the decision-making process might require more objectivity. I believe that probably the machine would be able to. Exactly.
Also depending on quality of data we have too.
So this is how the authors summarize the paper part of it. Then there are a couple of case studies given in the paper. We have just taken one for our purpose, which is about dyadic improv interactions, which is actually multimodal study of conflictive versus friendly interactions amongst two people. So here we consider two human beings who are termed as stochastic machines, so they can behave independently or randomly. And we want to see how behavior of one person impacts the behavior of the other, or predict somehow the way he will react after the first person has shown some behavioral traits. So the data consists of full body motion capture of interactions of two people. It is annotated by 3 experts, and it has we have considered the authors have considered audio features, pitch, energy, MFCC label 1 to 3. What Stefan said. The body language features such as body posture, velocity, orientation, and then they map these features into low-level descriptors such as cosine of body angle, cosine of face angle, average velocity of the right and left arm, the relative velocity of the two bodies, the two people. And they build a Gaussian Markov model based on these features to the human behavior, the second person's behavior. Gaussian mixture model. So they've got pretty interesting results. The authors were able to predict to a pretty high level of accuracy the feature vectors for friendly interactions than conflictive interactions. And one future work for this is how a virtual human can interact with for like a person or another virtual human. So let's say you have a direct interaction with a virtual human, how he should respond. So yeah, this is it. Any questions?
So you guys had like 2 more challenges that you mentioned. So the second one was the partial data and the uncertainty. So does anybody have some solutions for that as well? Maybe what we saw just in the case study right there.
It's a pretty brief overview because the studies are really deep.
Yeah.
For uncertain data, we can keep a threshold, like if it is below some threshold, we can ignore that data.
Yeah, so that's uncertainty in the classifier, the model.
In the model.
Right, yeah. And then before the model, like, so with the documentary, we weren't in full agreement about like what was going on. We would never find out, like really, like we don't know their heart rate, we don't know, like we couldn't ask them right in the moment, like they might not want to say how they actually felt like. So we have also uncertainty in the label, for example, sometimes.
Can I quantify uncertainty? Means what level of uncertainty we can get?
Yeah.
Learn from uncertainties.
Yes.
In practice, we can use context as a parameter because if we know what was the background, like suppose before this something like this happened, and then based on that we can infer if this is a positive, like if it is a genuine expression or it is not a genuine, because right in the initial, like just before that frame, the person was having some different type of argument, and in that frame altogether your stance changed. So from this we can infer something about this is fake or.
But if you don't have access to the context, sometimes so we're gonna get into that a bit more later. There's a whole class of machine learning algorithms that deal with uncertainty, and they're both probabilistic, but they're also these fuzzy machine learning algorithms that can use these uncertainties. Then how do you like
encode the uncertainty?
Right. So you can have like multiple labels at the same time. So you can have anger and sad at the same time, but with different like support or different membership assignment. Like that's how they call it. So it could be 70% anger, but it could be 30% sadness. So these are the different ways to encode these things. But then also, like with respect to partiality or like partial availability of data, I think we talked about that before, where, for example, I said when you have the hand in front of the face, you don't see my mouth, right? But maybe you can infer my emotion still through the voice that you have access to, because the voice isn't stopped by having a hand. So multimodal is a way to deal with partial data, and the case study did multimodal analysis. They had voice, they had face, they had gesture, and so on. What was the third challenge?
Subjectivity of behavior.
Yeah, so that's kind of like uncertainty as well. Yeah. Okay, let's thank the group and then. You might just don't want to mirror it or...
Good morning everyone. My name is Vaishnavi and this is Sarvatam. And today I'm here to talk about a paper by Mihalis, and he has made a study on the prediction of affect, which is spontaneous. So we cannot ask ourselves what is affect. So what according to you can be described as affect in plain English? Any thoughts? Yeah, just like, if you can just say it could be like the observation as a result of an action. That's what a normal dictionary would tell us. But in psychology, affect has three different definitions. It has categorical, dimensional, and appraisal-based definitions. In the categorical definitions, affect is said to have like 6 definite states, like happiness, sadness, fear, etc. These are said to be like independent of each other. And in dimensional definitions, these states are said to be slightly dependent on each other, and they're measured using 2 measures called valence and arousal. And as we know, valence is the positivity or the negativity in a person's emotions, and the arousal can be described as how active or passive a person is. And appraisal-based is completely dependent on the subject. So if you're given an event, if the subject is given an event, his reaction is what tells us the appraisal is. So once we know what affect is, we can go to studies on affect recognition. So what used to happen in the past is people used to concentrate on post expressions. And what I mean by post expressions are their discrete and basic emotion types, such as consider an example of a picture. So if a person is, if I had to predict what emotion is displayed in a static picture, this would come under post expressions. But the studies today are being migrated towards spontaneous expressions. Here, let's consider a video as an example. If I had to say what is the emotion of a person who is enacting in a video, this has to be done in like real time. Since and this is like a continuous study. And this paper is one such study on a spontaneous expression of, let's say, a given video. And how this paper is different from previous related works is that it differs in every aspect of machine learning, such as testing methods, training methods, the underlying basic emotions, the models used, and the kind of evaluation methods. How these are different is what we are going to see in the further slides. So the main points that have to be that are worthwhile mentioning here is that the predictions are supposed to be dimensional, continuous, and automatic. This means that the valence and the arousal are based on visual and audio cues. Another point that the paper makes is that they come up with a framework that integrates a temporal correlation between valence and arousal. This further helps us improve the predictions of a given reaction. The overall outline of the methodology proposed in the paper can be listed as pre-processing and segmentation of data, picking out the features, and then finally the actual predictions. So before the pre-processing, we need to gather the data set. Some of the main challenges that that Mihalis faced while gathering the data set was as follows. One was reliability of ground truth. So since the annotations have to be done by human coders, we always find disagreement between the coders. So instead of just finding means, one of the solutions that Mihalis found was he had to standardize the data by finding like a synchronization between these data points. Another challenge that was faced was the baseline problem. So when I say baseline, it is used as a metric for comparison of data. So what used to happen in discrete comparison was we used to have like multiple frames. So we knew what frame was before, what frame was after, and what is the current frame. But in continuous videos, we won't have such transitions. So in order to have this kind of a comparison, we define something called to emotional state and a from emotional state. So this way we can define a baseline and then have comparisons. Another challenge that was faced was unbalanced data. So in case we have too many positive results or too many negative results, the learning can be skewed. So Mihalis thought the segmentation can be automated, and before the process started, he wanted equal number of positive and negative sets of data. So once the data set was
So how do you balance the data?
I'm sorry?
How do you balance the data? So they want they want same amount of negative and positive frames or samples. Like, how do you do that?
Maybe discard selective samples.
Okay. Now you have less data.
Or
Random sample. Replicate some
positive samples, yeah. That's another one. Then I think what you were, so in like deep learning, often one of the things that people do is like use mini batches where data, like you only sample like 50 samples from your entire data set, and there you can choose to have them balanced, right? And so in the end, you're upsampling like positive samples if you try to balance your mini batches and stuff like that. So there are multiple methods to do this, and yeah.
So putting all these strategies together is what the pre-processing stage consists of. So we basically had to minimize the encoder disagreement, list out all the frames and define the do transitions and the from transitions, and do the actual optimal segmentation for getting the balanced data. So once the pre-processing was done, Mihalis had to identify features. So here the features considered were audio features and visual features. As far as the audio features, the energy of the signal and the pitch of the voice were considered. And for the visual features, as you can see in the pictures here, there were 12 points recognized on the face for facial features, and there were points on the shoulders recognized with shoulder movement. So these were like the main cues and features considered for modeling. And the next step is the actual prediction. There were two major methods that were tried out in this paper. One was bidirectional long short-term memory neural networks. This is much better than the normal neural networks because this can have temporal dependencies for a much longer time. Also, this is better than monodirectional long-term neural networks because this can learn from characteristics from future and past contexts. Another method that was tried here was support vector regression.
Can I ask like briefly what you guys think? So bidirectional LSTM, they can learn from future and past. If you have a continuous emotion recognition problem, do you have access to all of this data? Like, so somebody's standing in front of the computer and the computer wants to know what their emotion is, and like we use bidirectional LSTMs. So what do you need to do to like be able to use those?
Well, we need to interpolate or summarize the Lego.
So yeah, so you capture data continuously, right? And you can only make a decision on like something you've already seen, right? So the future becomes the past. So like they lag behind with their decision of like what actually happened. So it's just something to keep in mind. And yeah, so they always like move behind while you're already behaving over here, they're making decisions over here, right?
Okay, so do you have anything to say? Another method here that was tried out was support vector regression. This was mainly used because it promised optimal results. It was a convex optimization nonlinear function, and this always has promising results because we know that it leads optimal results. The evaluation for these strategies are as follows. There were 3 different types of evaluations that were considered. One was called RMSE. Excuse me. RMSE stands for root mean squared error. This is based on variance and bias, and it was mainly selected because it had the same units as the actual data. Although this does not provide us a structural correlation between the ground truth and the prediction obtained, and hence they had to come up with another evaluation strategy to find the correlation. Another evaluation method that was proposed in this paper was a relation between temporal and the valence results. So this is called emotion prediction specific evaluation. So this studies how positive or how active the reaction is, and measures the correlation between prediction and the ground truth. So the experimental setups were as follows. there was a setup called single cube prediction, where the predictions from each cube were fed separately to the machine learning algorithm. Feature level fusion consisted of getting features from multiple cues and forming a huge combined feature and then feeding this feature to the machine learning algorithm. Model level fusion consisted of getting separate cues from separate modalities and then combining all the results to a separate result in the end. So the results for these three separate, let's say, experimental setups whereas we could learn the following things from the results. Out of the single cues, we could see that capturing temporal correlations and remembering them was like a huge important task. And feature and model level fusion techniques showed us that visual cues provided us much better information about the prediction more than the audio cues. And overall, we could say that the entire result obtained was much better when all of these three cues was considered together. And as a conclusion, we can say that the system developed in the paper was a much better judgment of a prediction compared to a human judgment. And to intuitively understand what this application does, I have a video. So this is a game where a robot tries to mimic a person. So so you can see how. So this is a game where the robot tries to mimic the expressions of that person. You can see on the computer screen about how the face is studied on the computer screen. So he's trying to laugh here. So the robot actually said, I'll try to mimic you, and said, watch me and try to laugh. And then it actually asserts it and says, was that right? So that is like an intuitive way of trying to understand what this might do. And from this we can see how this can be applied to other domains like, let's say, for interviews or psychiatrists, for therapy or other applications like that. And challenges with this will be continued by Stefan.
So I'm going to discuss about what are the challenges which comes with affective computing. So before that, what is actually affective computing? Does anyone know? Like, have an idea? What does affective computing mean?
Incorporate emotional aspect in the machine's decision-making process so that it can behave more human-like.
Yeah, exactly. That's what it is. So, affective computing is basically making machines to interpret, recognize, and to simulate human effects. So, in short, it is like a machine should have some emotional expression and also have a feeling associated with it. So, let's see an example where. So, this is the Macintosh startup screen way back in like 90s and the earlier version of Macs. So this was the startup screen it used to show when the Mac was booting up. So you can see over here when everything is going fine, you can see a smiley face, like there's a two-face which is smiling. So this shows that everything is going well, it's booting up properly, there's nothing going wrong. And a fun fact is that the face, it's actually inspired from the Batman's Two-Face character. In the Batman's Two-Face character, one is like sad and one is like happy, but this is both are happy. So this logo is now in the Mac Finder, the file system. So when there was some error in the hardware, or if it is not able to boot up, it used to show this like a sad face, saying that it's some error happened. So do you think this is an example of affective computing? Primitive one, yeah. So what is missing in that? Like, it is showing some expression that something is going good, something is going bad, but what is missing in that? Why it can't be called as effective computing?
The machine doesn't know
one keyword which is missing.
It's not human-like.
Yeah, there is no feeling towards it. So there is no feeling towards it. It's not.
It's an expression.
Yeah, it's just an expression, exactly. So there is expression but no feeling at all. It's not, the computer is not happy or sad that it's, it booted well or it crashed. So that's what affective computing is, having both the expression and feeling towards it. Can you give me an example where this can be used, like an application where both expression and feeling will. Sorry.
Like medical, psychiatric practices in therapy.
Yeah, like real, like virtual human conversations. So if you are building a realistic virtual human conversation, if you are happy, then even the virtual human's voice should change, should match your this thing. And if you're talking about something really seriously, the virtual human can't be like laughing and make fun of you. So that's what even the most of the voice agents we have, like Siri and all, they still speak in a robotic tone. It's like even if you ask a funny question to Siri, it will say ha ha, and there is no actual feeling to it. So in these scenarios, affective computing will be much better. So I'm going to talk about 5 affective computing challenges. The first one is, as you know, the emotion is has a lot of modalities. Like for an emotion, there are a lot of factors. It can be even physical. It can be even there can also be some chemical factors like blood chemistry, brain activity, neurotransmitters. So to exactly gauge an emotion, we need all these modalities, and it is really hard to collect data for these modalities. So that is one of the challenges. So the second challenge is emotions are really hard to label. So emotions are both continuous and discrete. So discrete in the sense it can be happy emotion, it can be a sad emotion. But there are also a lot of emotions which vary between happy and sad. So some person can be neutral, and some person can be like the person itself doesn't know what he will say. So emotions are really hard to label. So the paper uses an analogy like emotion can be compared to like a weather. So weather has a lot of parameters like humidity, temperature, which says what type of weather it is. If it is a thunderstorm, there will be like a lot of rain, there will be a lot of humidity, there will be a lot of wind velocity. Or if it's a sunny weather, the temperature will be high, and those are only the extremes are labeled. But there is no one labels a weather like if it is sunny, if it's not too hot. There is no label for it. So only the extremes. Okay, it's really hot or weather. So that exactly. So that's what, like, emotions are only can be labeled at the extremes, but not at the intermediates. So it's good that computers can recognize these extremes. So we can't expect the computers to recognize all the range of emotions, but it is good if it recognizes the extremes and does something on it, rather than going very much detail into this expressions. So another challenge is the affective modeling. As we know that emotions are really highly idiosyncratic and highly individual, depends from one person to another. It's very difficult to model. Even there are few models, but most of these models are created in laboratory conditions, so they are highly pseudo-digital and they don't represent the real world. So one way to tackle this problem would be to see the human and animal models, like how they convey their affections and emotions, and build like a simulation on top of it. Even this will suffer with few predictions which are not nature-like, but it's actually a little better than having this stereotypical model. So I want to play a video where there is this robot in MIT called as the Leonardo. It basically
No, I'm there.
So this robot basically mimics a human. So let's just watch this video.
Leo, this is Big Bird. all yellow and fluffy? Hey Leo, look at Big Bird. Hey Leo, look at Big Bird, isn't he cool? Leo, this is Cookie Monster. Can you find Cookie Monster? Leo, Cookie Monster is very bad. He's very bad, Leo. Cookie Monster is very, very bad. He's a scary monster who wants to get your cookies.
So what you saw is like two examples where he showed an object and it learned by his voice and saying like he was with the big bird he was like continuously appraising it like okay this is a big bird and it's so good, but at the Cookie Monster he was like saying it's very 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 bad and it learned from that and showed appropriate emotions. So that is one of the like good demos where we can see affective computing at play. And so another challenge is they see that emotion expressions usually they see like for an effective emotional expression there should be a physical body because you need even body language to convey a good emotional expression. But most of the times the computers don't have any body at all. There might be a few humanoid robots which have hands and legs which can show appropriate emotions. So the paper says that it need not have any body, but there should be some way where you can effectively give out emotions. Like R2-D2 in Star Wars, it didn't have any. It did have a body, but it didn't have any like moving arms and all. So, but it used to effectively communicate its emotions, expressions by the means of voice. It used to make some voice to when it's happy or when it's sad. So, if you find a particular way in which we can communicate emotions, then it's pretty good. It need not be like hand gestures or movements or something like that. And also the emotion should be displayed at the right time. So, do you guys know what is this? What is it called?
Paperclip.
Clippy, yeah. Where was this used?
Microsoft Word.
Yeah. This was, I think, it's before the XP version. So what used to happen is, this was actually the Office Assistant. So this used to pop up when users are really frustrated, when they can't figure out what they want to do. So and when they are like banging the keyboard and figure out what is happening, then this used to pop up and used to dance and smile, like saying some help text. Do you want to know like what to do in this scenario? So most of the people used to find this really annoying. So the Microsoft thought that this would help people, but when they saw that when they saw the statistics and when they saw the usage, most of the people were just disabling this in the first try itself. So because people perceived it as like this thing is making fun of it because they are really angry and they can't figure out what they want, and this is like jumping around with animations. So this is like a very bad example of when to and even Microsoft jokes about this. So after in the versions of XP they just got rid of this. And the last challenge is in HCI. So just because human interaction is has a lot of emotions, doesn't mean that all the computing application should have emotion in it. We shouldn't force anything into this. So if there is an application which is purely logical and which does its purpose, then there is no need of any emotional reactiveness which can be added. So that's what for an application, if an emotional output is added, then it should be very effective. It should actually help in communicating it better, and it also should know when to give out these emotions and when to control this emotion. So yeah, those are the things which challenges which affect